Welcome to Tomorrow Unveiled. For what felt like, well, forever, really, the whole idea of a truly autonomous humanoid robot seems stuck. Either locked away in these super expensive university labs or, let's be honest, starring in those carefully polished YouTube videos, lots of hype. We spent so much time talking about the potential, always asking when, but it never really felt like now. But our dedicated research team, the ones who compiled all this information for us, they've been looking really closely at the past week, specifically October 28th to November 4th, 2025. And they're pretty unanimous. This week wasn't just another small step. It feels like the definitive end of that lab-only phase. Humanoid robotics just stepped over a huge commercial line. The race is, officially on.
Yeah, and commercial is the key word there. Because what the data is showing us isn't just, better tech. It's a massive shift. We're talking real market competition, real stakes, and crucially, robots you might actually be able to buy soon. The core insight from our analysis is that this isn't one big wave lifting all boats. No, the market's actually splitting. We're seeing this profound split, a kind of great bifurcation happening right now.
That split. That's really what we want to unpack in this segment of Tomorrow Unveiled, because it seems like the central conflict, the thing that's going to shape the whole robotics industry going forward, it's this clash between the super high cost, aiming for AGI Generalist robot versus the much cheaper, accessible product design for today's market. It's a fundamental difference in philosophy, isn't it? And it affects everything: hardware, AI, cost, everything.
Absolutely. Before we get into the specific companies, though, we need to properly define this humanoid schism, as we're calling it. For ages, it was simple. If it walked on two legs, it was a humanoid robot. Easy. But looking at the data stack we reviewed, that label just doesn't cut it anymore. These machines are heading down two totally different paths based on what they're for, and maybe even more importantly, how much they cost, and interestingly, how much failure they can tolerate in the design.
Exactly. It boils down to what you're trying to build first. Is the main goal to crack general intelligence? Or is the main goal to actually sell robots, like right now at scale? That decision changes the entire engineering approach, especially how they deal with things going wrong.
Okay, let's look at track one first. This is what the researchers are calling the AGI Generalist. You could call it the long bet. And the goal here is, well, it's huge: building genuine, embodied artificial general intelligence. In this vision, the robot itself, the motors, the frame, the shell, that's not really the end product, it's just the vessel. The hardware platform the AI brain needs to learn and operate out there in the messy, real world.
So when we say AGI generalists, we're thinking the big names, right?
Yeah.
Tesla's Optimus, Boston Dynamics with Atlas, Figure AI, those guys. For them, progress isn't measured by how many boxes they ship. It's about advanced skills. Can the robot learn a new task on the fly? Can it handle a place it's never seen? Can it understand context? That kind of thing.
And because that hardware needs to eventually support real AGI, the cost is just inherently high. We're seeing projections starting at, what, $20,000 and going way up from there. Puts them in the category of serious industrial gear or maybe specialized research tools. The timeline for their big goal, definitely long-term. They're banking on the AI itself, like Tesla's Grok 5 they keep talking about, getting exponentially better to eventually make that huge upfront cost worthwhile for industry.
That $20,000 price tag in the long view, it also means they can't afford many failures in the design, right?
Yeah.
Like if you're building $1 million prototype, a track one system, and it face plants, that's a disaster. Huge loss of money, data, time. So you have to build it incredibly robustly, highly integrated, top of specs from the get-go.
That's the crucial difference. Now flip to track two, the accessible product. This is the near-term bet. This strategy is all about getting into the market, creating something low-cost, mass market basically now. This robot isn't trying to solve AGI tomorrow. Nope. It uses more specialized AI, maybe feature-specific models, often leaning on things like large multimodal models, LLMs, to handle a limited set of tasks, tasks that are useful today.
Right. This is the track focused on getting adopted quickly, democratizing the tech. The cost targets are, frankly, kind of shocking. They're really aiming for under $5,000. That puts them squarely in reach of consumers, schools, hobbyists. The thinking here seems to be, get millions of these things out there. That volume will generate the data, it'll spark the ideas, maybe find the killer app for humanoids. Instead of waiting for that one perfect AGI breakthrough from the expensive camp.
And because accessibility is the goal, the tolerance for design failure is much, much higher. If a Track 2 bot breaks an arm, it's not the end of the world. It's maybe like a broken toy or a module you just swap out. The focus shifts completely. Away from that integrated, super expensive complexity toward something robust, yes, but also modular and easy to mass produce. They want these in classrooms, in basements today, gathering basic interaction data, building up a community of developers.
Okay, so this philosophical split, this bifurcation, it hit the market hard this week, starting with 1X Technologies. They just opened pre-orders for their NEO humanoid. Really testing the consumer waters, our research team flagged the price point, $20,000 up front, or you can rent it for $499 a month.
Yeah, calling NEO the world's first consumer-ready humanoid at 20 grand. That's a bold move, a big gamble. But you look at the hardware choices, you can see they're serious with a consumer angle. It's about 5'6" mesh, and it's relatively light at 78 pounds. And it uses this proprietary tendon drive system. It's a very deliberate choice. Tendon drives mean smoother, quieter movement compared to rigid gears. And critically, NEO has a soft body made of polymer compounds for safety.
That soft body. You really can't overstate how important that is for a home robot, can you? An industrial bot needs to be rigid, powerful, but something in your house. Safety first. If an Optimus V3 arm hits a wall, the wall might lose. If NEO bumps into you, the idea is everyone walks away okay.
Exactly, and their ambition is huge, targeting 10,000 units for delivery in 2026. That's astronomical compared to the handfuls the AGI labs are making right now. But there's a big catch, a really big catch, tied directly to how they plan to get their AI trained.
Right, the catch. They're being very open about this expert mode, the human teleoperation system. It's not just a fallback, it's core to the strategy. The research team called it a kind of social contract with the early buyers.
Basically, you pay your $20K or your $499 a month, and you agree to let human pilots sometimes take control of your robot remotely, like a ghost in the machine. Why? To train the AI. It's a way to harvest really high-quality, real-world training data directly from people's homes and workplaces. It captures all the messy stuff, friction, confusing instructions, unexpected obstacles, things the simulation might just miss entirely.
Okay, so 1X is pushing the upper boundary of accessible at 20K. Then this other announcement comes along from the Chinese manufacturer Noetix. And they didn't just undercut the market, they basically took a sledgehammer to the price floor, the Noetix Bumi. This thing completely reset expectations for what a mass-market humanoid could cost.
Oh, absolutely. This is less about tech specs and more about an economic revolution. The Boomie came in at roughly 1,400 US dollars. It's just under 10,000 yuan, or 9,998 RMB. That price point is. It's monumental. It instantly shifts the whole conversation away from complex industrial ROI calculations and just slams it down onto pure accessibility.
It feels like the humanoid equivalent of the Raspberry Pi or the Arduino moment, doesn't it? Suddenly, high schools, coding clubs, university labs that could never dream of a $20,000 robot, now they can actually get their hands on a functional bipedal platform. So what do you actually get for $1,400?
You get exactly what that Track 2 philosophy promises: accessibility over raw power. The Boomie is deliberately small, almost child-sized, about 3 feet tall, weighs only 26 pounds, designed to be non-threatening.
Yeah.
It has 21 degrees of freedom, or DOF. That's enough for it to walk, balance itself, do some basic interactions. But it's explicitly not designed for heavy lifting or factory work. It's built to be programmed, to be experimented with, to collect data.
It's the pure expression of that Track 2 idea. Get the hardware out cheap, get it into millions of hands, and let the community figure out what to do with it. Let them find the killer app through sheer experimentation. But let's swing back to Track 1, the AGI Generalist camp. There, the focus is still laser sharp on capability, almost regardless of cost.
Precisely. Take the upcoming Tesla Optimus V3, still projected to land somewhere between $20,000 and $30,000. It remains the sort of hardware pinnacle for the AGI track. But the most critical detail, the thing our research team really zeroed in on, isn't speed or battery life. It's the hands.
Right. The report highlighted Tesla's plan for 22 degrees of freedom in the hands alone for V3. For listeners maybe not deep in robotics, can you unpack why that jump is such a big deal?
It's a massive leap towards human-level dexterity. Think about it. The human hand, probably the most complex tool nature ever made, has around 27 degrees of freedom. The previous Optimus prototype, V2, had something like 11 DOF. You could grab stuff, sure, but no fine motor skills. Jumping to 22 DOF, that means the robot can start to mimic the really subtle movements, twisting, fine gripping, sensing pressure that humans do without thinking. So that 22 DOF, it's basically the physical entry ticket for AGI, isn't it? If the AI, like Grok 5, is ever going to learn real human tasks, folding clothes, plugging in tiny cables, using tools delicately, it absolutely needs hands that can feel and manipulate things with that level of precision. Couldn't have said it better. The hands are the sensors in many ways. If the AI doesn't get that rich multimodal tactile data stream back, how much pressure does it take to hold an egg versus a brick? It can never achieve general intelligence in the physical world. That 22 DOF hand is the physical key needed to capture that data, to finally bridge the gap between digital thought and physical action.
Okay, so you have this increasingly sophisticated hardware, whether it's the $20 KNEO or the $30 K Optimus V3, but to make it actually do anything useful, the AI driving it needed some major breakthroughs too. The news this week wasn't just about hardware, it was full of announcements about AI that's focused on action, not just conversation, moving from talking to doing.
Exactly. We're seeing a real shift in the industry, moving beyond large language models, LLMs, which are great at text and chat, towards models that can actually control a physical body in the real world. Let's start with large behavior models, or LBMs. These have been pioneered by groups like the Toyota Research Institute, TRI.
Okay, LBMs. How are they different from the LLMs we hear so much about?
Think of LBMs as like the language models, but for physical actions. They don't just process words. They take sensor input what the robot sees, feels, senses nearby, and map that directly to complex physical movements. Traditionally, you had to painstakingly code every single little behavior. If object is X distance, move arm Y speed, stop at Z coordinate. LBMs aim to get rid of that. The robot learns by watching a human do something, like sweeping dust off a table. And crucially, it learns the concept of cleaning, not just that one specific motion. So ideally, it can then figure out how to use a mop or a cloth for a similar task without needing brand new code for every tool. It generalizes.
That sounds powerful. And it connects directly to the other big AI buzzword we saw, vision language action models, or VLAs.
Right, VLAs are kind of the integration layer. They take the visual understanding, the vision, and the language comprehension, the language that LLMs are good at, and they connect it directly to the physical control, the action needed by the LBMs. So you can give the robot a complex natural language command, something like, hey, grab the blue mug, the one next to the newspapers, and put it on the top shelf.
Then,
The VLA uses its world knowledge to understand the objects and the goal, and then translates that into the precise sequence of movements. Walk over, identify the mug, grasp it correctly, navigate, lift, place it down gently. It links understanding the world with acting in it.
Okay, this is amazing progress on the AI side, but it brings us right back to what feels like the biggest problem, the core conflict in the industry right now: data, specifically physical data. LLMs had it relatively easy, didn't they? They could just ingest the entire internet, vast amounts of text data, pretty cheap to get. But AI models for robots, they are starving for physical intelligence data. The real world is messy, physics is tricky, and getting data on how to interact physically, safely, complexly, it's incredibly slow and expensive.
That's the crux of it. Physics is hard. You can train a model perfectly in a simulated world, but then in reality, maybe the floor is slightly more slippery, or the object weighs a tiny bit more, or the robot generates some unexpected momentum turning, and the whole thing fails. Our research team basically identified 4 main competing strategies that companies are betting billions on to solve this physical data problem. 4 very different approaches.
All right, let's break them down. Strategy number 1, the big, bold one, the simulation bet. This seems to be primarily Tesla's game with Optimus and Grok 5.
Yeah, Tesla's approach is audacious. They're essentially trying to bypass most of the messy, real-world training. They're betting everything on creating this incredibly detailed, unified world simulator. And the key is, it's trained on the massive, unique data stream from their full self-driving FSD cars. Years and years of real-world video, depth perception, how things move, data no one else has at that scale.
So the theory is, if Grok 5 can learn super complex driving dynamics, figure out pedestrian intentions, understand 3D space really well inside this hyper-realistic simulation, then that intelligence will just transfer smoothly over to the Optimus robot, reducing the need for endless hours of physical trial and error.
That's the billion-dollar bet, yes. Seamless transfer from sim to real.
But hang on. Historically, that sim-to-real transfer has been notoriously difficult, right? We've seen it stumble in drone navigation, early self-driving attempts. How confident are the researchers, based on the internal docs, that Tesla won't just hit a massive wall here, that Grok 5 won't be brilliant in the simulation but clumsy in reality?
That is the central risk, and the internal documents acknowledge it. Tesla's confidence really stems from the sheer scale and, they argue, the real-world grounding of that FSD data. It's not just abstract simulation. It's simulation built on terabytes of real driving. They believe their continuous virtual environment with its sophisticated physics modeling will be good enough. But if they're wrong, they could end up with an AI that's incredibly smart but physically incompetent when faced with, unexpected friction or a slightly heavier object. It's a huge gamble.
Okay, so that's the simulation bet.
Yeah.
Now, moving to almost the opposite end of the spectrum. Strategy 2, the one used by 1X, the Tele-operation Bet.
Exactly. Companies like 1X with their expert mode, they're banking on humans driving the robots remotely. Research like the H2O project, which showed real-time humanoid control using just a regular camera and AI, proves this can work at scale. Why is this data seen as superior by this camp? Because the human pilot instantly provides high-quality, perfectly labeled real-world motion data. It includes all the little corrections needed for real physics, the stuff simulation struggles with.
So it's not just raw data, it's corrective data, data that shows how to succeed in the messy real world.
Precisely. It costs more per data point, probably, because you need human pilots.
Yeah.
But the data you get is arguably more reliable. It's ground truth for successful movement in that specific environment. The human ensures the task works, and the AI learns from that success.
Okay, strategy 3. This one's favored by companies like Figure AI. Our team called it the human observation bet. They mentioned something called Project Go Big.
Yeah, this approach is fascinating. It relies purely on observation, but at a massive scale. Figure seems to be betting on building this enormous library of first-person video. Think, thousands of hours of workers wearing GoPros, doing every task imaginable, folding laundry, stocking shelves, using tools, cooking.
And the goal is something they call zero-shot human-to-robot transfer. Can you break that down? What does zero-shot mean here, practically speaking?
It means the robot doesn't need to practice the specific task beforehand. Instead, its AI studies that huge video library of how humans move the kinematics of folding a towel, for instance. Then, when asked to fold a towel, it finds the closest human example and tries to map that motion onto its own body, its own joints and limitations. It's learning by watching, essentially, trying to generalize human movement patterns to its own form factor. It's a lower-tech data collection method, just video, aiming for a very high-tech, generalized AI outcome.
Interesting. Okay, one more strategy. The research team called this one the hybrid bet. Companies like Nura are using this. Seems like the most pragmatic approach.
You could say that. Nura basically looks at pure simulation and pure real-world testing and says both have big flaws. Simulation isn't real enough. Real world is too slow and expensive. So their answer is the sim-to-real gem. They train the AI mostly in simulation where it's fast and cheap. But then they constantly test that simulation-trained AI on physical robots in a dedicated controlled testing facility.
And how does it learn and improve in this hybrid model?
Failure is the key. When the robot inevitably fails in the physical gym, maybe it drops something due to momentum the simulation missed, or its grip slips on a smooth surface, that failure isn't just noted, it's quantified. Sensors measure the exact forces, the material properties, the friction coefficients that caused the failure. And that specific real-world failure data is immediately fed back into the simulation engine to make the simulation itself more accurate. It creates this tight loop, this automated flywheel. Test in reality, find flaws, improve simulation, train better AI, test again. It tries to get the best of both worlds, rapidly closing that gap between the virtual and the physical.
Wow. Okay, that's a really fascinating look at the different ways these companies are tackling the absolute core challenge right now. It's not just about building the robot. It's this intense data war to figure out how to make it truly intelligent in the physical world.
Yeah, it really highlights that the race isn't just hardware anymore. It's about who can acquire and effectively use the right kind of physical data the fastest to solve that AI bottleneck.
If you're finding this glimpse into the robotics data wars insightful and kind of mind-bending, please take a moment to like this video, subscribe to Tomorrow Unveiled, and maybe hit that new hype button. It really helps us reach more people curious about the future. And definitely turn on notifications so you don't miss our next update.
And if you happen to be listening on a podcast service, maybe Apple Podcasts or Spotify, we would be incredibly grateful if you could leave Tomorrow Unveiled a rating and a quick review. It genuinely makes a difference in helping new listeners discover the show.
All right, so we have these competing strategies for intelligence, but where are these robots actually showing up? They're leaving the labs. Where are they going first?
Well, the overwhelming consensus from the industry analysts our team looked at points to one main place right now: automotive manufacturing.
That makes a lot of sense. Car factories are highly structured, predictable environments, relatively speaking. And maybe more importantly, the auto industry has these really persistent, well-documented labor shortages. They need automation. Even if it's expensive initially, it's a perfect test bed.
And the results coming out of these early deployments are starting to validate that whole expensive AGI Generalist approach. Take Figure AI's work at BMW's plant, their Figure O2 robot. The data shows it achieved a 20-hour continuous shift doing autonomous parts handling. This wasn't just a quick demo for the cameras. This was sustained, real industrial work over a long period.
And the performance improvements, the metrics the research team cited were pretty staggering compared to earlier tests, weren't they?
They really were. They reported 400% increase in the speed of completing tasks. And maybe even more critical for a factory floor, a 700% improvement in task success rates, meaning far fewer errors, far less need for humans to step in and fix things.
That 700% number, that speaks volumes about reliability, doesn't it? It suggests these humanoids can reach the kind of dependability needed for industrial settings, at least in these structured environments with enough training. It shifts the question from can it work to, okay, how fast can we scale this deployment?
And we're seeing this across the board with the big players. Boston Dynamics, famous for the backflips, their Atlas robot is now demonstrating actual autonomous factory work too, moving engine covers around using those large behavior models we talked about. The key takeaway is they're moving beyond just the cool, carefully choreographed demos into flexible, real-world tasks that aren't perfectly pre-planned.
And it's spreading through the supply chain. Foxconn, the giant manufacturer, is starting to integrate humanoids at their AI server factory in Houston. They're using NVIDIA's big AI foundation model, the Isaac GR0DT N1 platform. That's a huge signal, right? Foxconn moving from traditional fixed robotic arms towards more flexible humanoids suggests they see a real advantage in robots that can adapt quickly to changing production lines without needing massive retooling. That's a big potential win for efficiency.
It is, but every time we talk about the promise of the generalist humanoid, we have to inject a dose of reality. The research team consistently flags this counter-argument. Specialized robots are often still the better, more efficient, and more profitable solution today.
Ah, yes, the reality check. This is the economic tension playing out right now. Humanoids are flashy, but non-humanoid machines designed for one specific job. They often just do it better and cheaper.
Look at Agility Robotics Digit. It's bipedal, looks kind of humanoid, but it's really specialized for logistics, moving boxes in warehouses. And according to our analysis, Digit is still basically the only humanoid-class robot out there that's confirmed to be consistently earning money for its work. It does a specific, valuable job reliably.
And then you have companies like DJI, the Drone Kings. They just released a robot vacuum cleaner, the Romo. But it's not humanoid at all. It has these specialized little robotic arms, specifically designed just for cleaning edges and corners really well. That specialized design is way more efficient, faster, and certainly much, much cheaper for that single task than trying to get a $20,000 general-purpose humanoid to do the same thing.
And that's the core tension, the problem for the AGI long bit right now. Why would a small business owner pay, say, $50,000 for a generalist robot that can sort of do 10 different things okay, when they could buy a $5,000 specialist machine that perfectly stacks pallets or cleans intricate floor edges all day long? Near-term efficiency and proven ROI, they still have a massive economic advantage over the promise of long-term generality, especially for smaller businesses.
So, to keep things grounded, let's quickly touch on the core technical hurdles that the research confirms are still holding back truly widespread adoption. Even with all this progress, there seem to be three big ones.
Yeah, first is what we can call the Dexterity Gap. We mentioned the 22 DOF hands on Optimus V3, which is great for movement kinematically, but that's only half the battle. Current robotic hands still really lack the sophisticated sense of touch, the tactile sensitivity, needed for genuinely delicate or complex assembly tasks.
It's the difference between being able to move your fingers and actually feeling what you're touching, right?
Exactly. Vision systems, the cameras, have gotten incredibly good. But tactile sensors, the haptics that let a robot feel the precise texture, weight, slipperiness, the pressure needed, they're still lagging behind significantly. You can teach a robot to see a tiny wire, no problem. But until it can feel the exact tension needed to strip that wire without breaking the copper strands inside, its use in things like electronics assembly or delicate repairs or even surgery remains pretty limited.
Okay, Dexterity Gap, number 2.
Power efficiency. Batteries. Still the Achilles heel of, well, pretty much all mobile robotics.
The eternal problem.
It really is. It comes down to the energy density of current battery chemistry, mostly lithium-ion. Most of these powerful humanoid robots, the industrial-grade ones, they only get about 2 to 4 hours of runtime before they need a battery swap or a long recharge. That's a major limitation for factories that run multiple shifts. Plus, these complex robots generate a lot of heat, so a chunk of that precious battery power is just wasted on running cooling systems, not doing useful work. Until we see a fundamental breakthrough in battery tech, maybe solid state or something else, the humanoid is kind of stuck with a short workday.
And the third big limitation.
Still the overall cost versus ROI for the mainstream market. Yes, the Boomie at $1,400 is a game changer for accessibility and education. But the reliable, capable industrial generalists, we're still talking $50,000 to $100,000 per unit. And that's before you factor in the cost of integrating them, training them, maintaining them.
That price works for giant corporations like BMW or Foxconn, maybe. But for the average small or medium-sized business,
Exactly. For most SMEs, the return on investment for a robot that costs as much as a luxury car, has limited battery life, and still requires significant programming or supervision. It's a very tough sell, especially when, as we said, cheaper, dedicated automation often already exists for their specific repetitive tasks. Either the price of the generalist has to come down drastically, or their autonomous capabilities need to jump up exponentially to make the math work for the broader market.
Okay, so let's try and pull all these threads together. This past week, October 28th to November 4th, feels like it genuinely shifted the robotics landscape. We've moved past pure research chatter. We're now talking about real commercial products, competing business models, actual price tags, and market strategy.
And the absolute defining feature of this moment is that market split, the bifurcation. We're seeing two parallel tracks, two possible futures unfolding at the same time.
Yep.
Track one, the big, expensive, long-term gamble on achieving true artificial general intelligence. That's your Tesla, your figure AI. They're focused on cracking the intelligence problem first, using that high-cost hardware as the essential platform for the AI to learn.
And track two, the accessible near-term product strategy, focused on adoption now. That's the 1X NEO trying to pioneer the consumer market, and especially the Noetix Bumi just smashing the price floor, prioritizing getting hardware out there cheaply, democratizing access, hoping volume sparks innovation, the Arduino moment, as you called it.
Looking ahead, say, the next couple of years, the immediate future is going to be shaped by who wins that data war we discussed. Which strategy simulation, teleoperation, observation, or the hybrid approach proves most effective at gathering that crucial physical intelligence data and bridging the sim-to-real gap?
We're seeing real validation in factories now, proving the generalist form factor can work reliably in structured settings. But getting to true widespread scale, that still hinges on overcoming those stubborn technical hurdles. Closing the dexterity gap in hands and, critically, solving the battery life problem.
Absolutely. And this whole conversation, it really throws a spotlight on a huge challenge that isn't purely technical. It's the perception gap. Just this week, we saw this completely fabricated story about some kind of biomechanical pregnancy robot in China go totally viral online. Pure science fiction hype, generating clicks and maybe fear.
Right, I saw that. Wildly exaggerated.
Meanwhile, what's actually happening in top research labs, they're working on incredibly hard foundational problems. Like MIT just published work on a system called Context. Its goal: to help a robot understand a simple but context-heavy command like, "The tool I just put down over there is my tool. Don't touch it."
That seems basic, but teaching a robot that kind of contextual ownership and intent, that's fundamental for safety if they're going to work alongside people, isn't it?
Exactly. So you have the public consuming these over-the-top sci-fi narratives, and then you have the actual cutting-edge research tackling these painstaking, essential semantic and physical interaction problems.
It highlights a dangerous chasm, doesn't it, between the hype and the reality.
It really does. And perhaps the biggest challenge for the entire robotics industry moving forward won't just be building better robots or smarter AI. It'll be managing that huge gap between public expectation, often fueled by fiction, and the slow, difficult, essential research needed to make these machines truly safe, genuinely useful, and economically viable for everyone. That perception management, that communication challenge, that might turn out to be the toughest data war of them all.
We love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about the rise of the machines in robotics. Which track do you think wins out? The AGI bet or the accessibility play? Let us know.
Thanks for tuning in to Tomorrow Unveiled.
We'll catch you next time for the next segment of Tomorrow Unveiled.